Okay, so guys, let's continue our lovely and sweet control topic and of control. This is my favorite class among the vibration, robotics, and dynamics and modeling of physical. So I'm teaching too many things. When I joined this SDSU at 2014, I taught almost 6 courses, but this is my favorite one. So remember that we derived the equation of the motion for the most fabulous example, that is the particle pendulum, together in the last class. And you saw that, for refreshing your mind, we're going to continue. You saw that if the base of that has as the hip of your body has a displacement of x that is changing with time, and we derived together the equation of the motion, which was nonlinear, as theta double dot plus g over L sine of theta, that was non-linear differential equation. I told you the left-hand side always is the internal dynamics of the system. System behaves by itself. They had to learn this in your differential equation course. And right-hand side is, if I remember correctly from the previous class, look at your notes, okay? Correct me if I'm right here. It was like this, is right? Yes, guys? The right-hand side? So minus x double, hopefully this is like that, huh? Yes. Okay. So, and the right-hand side, I told you, is that the torque, external forces, control, command is the right-hand side, okay? Always, in any differential equation, okay? So this is nonlinear differential equation because of the sine of theta and the cosine of theta, because the nonlinear nature of those. And I told you, you can control, yeah, this is a simplified model of your leg to keep that at, say, you want to keep it at 45 degree. While you are dancing, ding, 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 by your hip joint, you want to keep that for the 45 degree. Remember Michael Jackson, what he's doing? So you have to apply a control torque to your hip joint, saying, to simplifying the problem, you understand. So we say a torque, I'm applying here tau. So I told you the concept of the course is to design this tau. Okay, today I'm going to go to the MATLAB and coding today. Okay, so based on this, I told you that I introduced you the block diagram and said this is the disturbance, okay, disturbance of the system that was, let me say this D, D was, I wrote here. And disturbance, you see that it takes negative, say here, because I'm going to do this in the Simulink, so I'm going to show exactly the same symbol for you, minus plus the control torque, so the control torque, the tau, I introduced you the block diagram, it goes inside your plant. Plant can be the temperature of the room, differential equation can be your car, can be a robot, can be Falcon 9 that Elon Musk today sent to the space station, can be whatever that you want to control. Okay, whatever. You want to control the pressure of a tank. So this is the plant, that's right. I told you this is the plant, or G. We're going to go to math in detail eventually. G. So it is theta double dot. I'm writing at the time domain, but I'm going to shift it to frequency domain eventually, Sine of theta. This is wrong. What I wrote here is wrong because we have to make it linear. But for sake of that, this going to gives you, I told you, a real angle of your leg of the pendulum, okay? And then I told you that you want to compare with that 45 degree, right? Okay. Theta desired, So when you do that, guys, sorry guys, okay? So you are comparing this, as I told you. Can you hear me? Yeah. I'm doing that. I see that. No, thank you. You know, I always am joking with my students. You know what is the first rule of my class? The first rule of my class: you cannot defeat me. I'm just joking. So you are comparing the desirable input with the real output. It sends you the error signal. We're going to go to math shortly in two classes, the next two classes. So based on this, you're going to design. This is the whole course about this part. Designing the controller like a lead lag controller or PID controller. I'm going to teach you eventually, okay? And this sends you the signal to keep that angle of the leg at 45 degrees. Okay, so I told you this is the feedback control. Okay, feedback because you're feeding back the real output to be compared with the desirable input of the system. And I told you this is input and this is output. These are the terms that you have to know. This is the error signal, as I told you. This is the plant, as I told you. Any plant. This is controller, obviously. And we had also the sensor that I'm going to teach you why we eliminate here, okay? To measure the real output, but I'm going to teach you why we eliminate here, okay? But we're going to derive the transfer function for that eventually, okay? And the disturbance, okay, of the system. Okay. This is the whole picture of the course that I taught you in the previous class that we're going to go in detail. But before going there, I have to teach you the fundamentals of the control about the stability. Because as I told you, the mission of this course is to stable and unstable system. What is stability? What is partial stability? Or marginal stability? Okay, and what is unstable system? So through this problem, this is very useful. Even that you go to grad school in Stanford, in I don't know, MIT, this is the most powerful example that you can make the people understand what you are talking about. Even you go to industry, okay? So we have to know about this. Another name of this is the marginal stability. So we have to know about this. Okay, this pushes us back to go to now to differential equation course of this equation. Okay, so guys, theta double dot plus g over L sine theta equals to, now forget about the control torque, okay, because I didn't teach you. You only have this system, x double dot over L cosine theta. If you graduate from SDSU and anybody asks you, can you find the analytical solution for this differential equation, you can say no. Why? Because this is nonlinear term. In the differential equation course, they taught you the linear differential equation. So you have to linearize this first. Linearize. I taught you in the vibration course in the previous semester. Using what? Using the Taylor series expansion. For those of you who are not in my vibration class, I'm teaching here, okay? Because any nonlinear ODE you get, first you have to use Taylor series expansion. Can I go to the next page? Yes, guys? Okay. So, what's that? It says that if you have a equilibrium point, first, any of you that you had vibration with me, so what's the definition of equilibrium point for a control system? This is super important concept even in the nonlinear control. If you go to graduate, if you go to the NASA, if you go to Tesla, what is the equilibrium point for the control system? Is as it names, is a point system is at rest. Is at rest. So let me take you back to the ME220 dynamic course that you passed. When I say the system is at rest, what is zero? You tell me. You are at rest right now. What is zero in you? What is zero? Okay, what? No, no. What property of your car? You park your car. What of your car is zero in dynamics course? When your car is parked here, position no. Yes, yes. Its velocity is zero. When you have no velocity, its acceleration is zero. Now we are dealing with the angular motion, theta double dot. This is angular velocity. That's right. So being said that means theta dot is zero at the equilibrium point and theta double dot is zero for any system. If I say for a thermal system, you are controlling the temperature of the room, equilibrium point is that, say, theta T dot is zero, theta double dot is zero. Okay, sorry, T double dot is zero. If your pressure P dot is zero, pressure of a tank, P double dot is zero. The term that they are changing with time, they are zero because your system is at the equilibrium point, is at rest. Okay, so let's go back here. So when I say theta double dot plus G over L sine of theta is minus X double dot over L cosine theta plus, there's no plus. First of all, when I'm talking about the equilibrium point, this is very important, guys. Means system by itself is zero, not based on the external force. What is the external force or torque or disturbance? Here. So you have to say system by itself. Only the left-hand side is zero, guys. Okay. This is, here we go. Okay. And physically makes sense because if you apply the X, the hip joint, does this your leg gonna remain at rest? No, it's gonna oscillate. That's right. So you have to remove it from the right hand side. So as I told you, the equilibrium point of the pendulum, moving pendulum, this is zero. Bye bye, zero. So you get this from here. You get sine of theta is zero. And you know that from the trigonometry, it is sine of k pi. K is 0, plus minus 1, plus minus 2, and etc., etc. So from this simple equation from kindergarten, you say we are showing with this star equilibrium point, we are showing with the star, like the temperature star equilibrium point, pressure star, I don't know, pizza star, if you want to find the equilibrium point of pizza or kebab, whatever, I don't care. So theta star equilibrium point is k pi, equilibrium point of this pendulum. But we have different, guys, we have different equilibrium points. Let me try one by one, few of them, huh? Let me say k is 0. When k is 0, okay, you get theta star is 0. Guys, look at here. This is the moving pendulum. It says your equilibrium point here, and there is no disturbance at the base. So if I leave it here, it's gonna remain there. That's right. Yes? Huh? Equilibrium point, because here is, see here, guys? Here is theta. Equilibrium point is so 0. This is 0. If I leave it here without an external force, it's gonna be there forever, right? Yes, guys? So system gonna be at rest. So this is a valid equilibrium point. The take-home message is that when you got different equilibrium points, you have to examine about the feasibility or acceptable or unacceptable equilibrium point. Does it make sense? You have to examine that. Don't say, oh, that's it. No. In different system, maybe Not the first one, second one is the equilibrium point, not the third one. See what I'm saying? Let us go stick to plus 1k. So if the k is plus 1, your equilibrium point gonna be pi. Okay, good. Let me show you physically. Here gonna be pi, 180. And there's nothing here. There is no friction, no control torque. If you put your pendulum here and release it, it's gonna remain there. It's gonna remain there. No, just try by your hand. Raise your hand to the upright position and remove any torque on your shoulder, guys. Right now, do it, and see it falls. Yes, everybody. Remove the torque, so it's not at the rest. So this is not acceptable equilibrium point. The same is valid for -1. If you say k is -1, it says equilibrium point is minus pi. Here is plus pi, here is minus pi. See? Again, it's not equilibrium point. Go away. So we're gonna stick to this. Physically, this makes sense. You are a graduate of mechanical engineering. You have to make logic, not based on gambling. Oh, this is what it is. I don't know why. Okay? After graduation, when you're working for the company, people pay you salary that you make a scientific judgment, not based on your guts. Say, oh, I don't know. See what I'm saying, guys? So, can I go to the next page? Yes? Yeah. So, we found the equilibrium point of this moving pendulum is 0. Now the Taylor series expansion says if you have a given function, I hope that you know it. If you don't know, I'm just refreshing your mind. As a nonlinear function of parameter x, you can approximate that as a linear function at f at equilibrium point of that x dot plus round f partial derivative round x at where? At the equilibrium point in 1 factorial x minus x equilibrium point plus round second square over round x square. Second partial derivative is at equilibrium point x minus x star, and you have 2 factorial here squared, and plus round nth partial derivative xn at the equilibrium point x minus x star power of n. This is Taylor series expansion. You can find it in the undergraduate math that hopefully they taught you. So I told you linear function, linear. Y is equal to x. In the previous class I told you y versus x. This is linear. Is this linear? Is this linear? No, that's parabolic. So after this point, we don't need these terms. Why, guys? Because it gives you x squared, x cubed, x4, xn. See what I'm saying? Yes, everybody? Yeah. Okay, so we're gonna remove the rest. Because we are linearizing our nonlinear differential equation to design controller for that. Here we go. So now I'm just doing this, and you can do the rest at home as homework for yourself. So what is our equation? Our equation is this: theta double dot plus g over L sine theta is minus x double dot over L cosine theta. We found the equilibrium point is 0. Based on whatever it said, you know that the sine of theta, we want to linearize this and this nonlinear terms, is going to be sine at the equilibrium point 0. Partial derivative of sine with respect to theta, our parameter theta, is cosine theta at where? At equilibrium point of 0, and here's theta minus 0. Sine of 0 from high school is 0. Cosine of 0 is 1. Theta minus 0. You can say, here we go. So at the equilibrium point of 0, you can memorize this forever. The sine of theta is theta. Maybe you know it. And this is valid, please accept from me, between 0 and 6 degrees. For a small angle of the pendulum, always this is valid. Please do at home. You can say cosine of theta radical point of the 0 can be approximated as 1. And the tangent of theta can be as say theta. Here we go. Simple like that. You don't need to do it every day. You have to know it by memorizing eventually. Being said, now we want to transfer everything as a linear differential equation. Theta double dot plus g over L theta. I'm changing signature with theta is equal to minus x double dot over L. Cosine of theta is how much? 1. Here we go. Now this is the linear differential equation from differential equation course that you had previously. I'm going to do it in MATLAB today. But before going there, I promise you that I give you the concept of the stability, partial stability, and instability, and instability in the system, in the control systems. Okay, if I make the right-hand side to 0, what's the name of this differential equation? This is homogeneous differential equation, remember? Because the right-hand side is 0. Homogeneous. So let us stick to that. What does it mean? I'm going to translate for you physically. I'm going to say, this is the pendulum, the same problem. I just remove the disturbance. Only I deflect from the equilibrium point and release it. Okay? And release it. Why I'm doing that? Because I'm teaching you about the stability, marginal stability, and the instability of the system. So, let us do that together. I'm saying, you know what, for now, when I go to MATLAB and coding, I'm going to include that and compare between the linear differential equation and nonlinear differential equation. You know that from the differential equation course, the homogeneous solution, means that the right-hand side is 0. I hope they taught you. Theta of t is EST. This is the homogeneous solution. So theta dot gonna be SEST. Theta double dot gonna be S square EST. Not magic. After this is the elementary school. Just replace here all of these. Gonna be S square EST plus G over L EST is 0. This leaves you EST S square plus G over L is 0. Fundamental questions. I taught in the vibration class previous semester. Can this be 0? This term? Exponential term? Can be? No, because if this is 0, your trivial solution is 0. Your problem has trivial solution of 0. This is ridiculous. This cannot be 0 logically because this is your solution. So this is 0. Okay? If this is 0, I'm just moving here. You have two roots, for God's sake. S1 and S2 gonna be sorry, let me write like this because you're gonna ask me. You're gonna have S squared is minus G over L. So we have two roots, S1 and S2 gonna be plus minus I, because root square of, we don't have that because you know that I is a complex number. Imagine it is root square of minus 1. I G over L. So you have a pair of, you're gonna listen, you're gonna hear these terms from me in this course a million times. You have a pair of pure imaginary roots. Later, we're gonna call these poles of the system in the control class. Poles in few classes. A pair of pure imaginary poles. Can I go to the next page?
Yes.
Sorry, guys. So now you have to get to know about the complex plane in the control class. Imaginary part of a complex number, real part of a complex number. If A is a complex number like as A plus B, J or I don't care. A is the real part and B is the imaginary part. So can I say here is A, for example, here is B. So this is the point A. Okay, this is how we show. Right? I know that you know it just for a question. So now you have a pair of pure imaginary roots or poles of the system on the imaginary axis. See here? On the I only, imaginary. So, and here is a, let me delete this. Here is plus G over L, and here is minus G over L on the imaginary. Okay? Means that here you have I. Eventually we are moving toward control. So our solution was this. ESD. You have two roots. I'm just putting here. A, E, first roots, I, G over LT, plus B, you have two roots. E minus I, G over LT. From here, see? Plus minus I, G over LT. Now you know that Euler or Euler formula that I bet you have seen this previously. This is E plus minus I theta. This is the general statement. Is cosine theta plus minus I sine theta. This is Euler or Euler formula. Here we go. Using that, you get the angle of the pendulum, assuming that there is no disturbance, assuming we do have. I'm going to teach in the MATLAB code. It's going to be a cosine G over LT. This is plus, so plus I sine G over LT. Now the second part, B, again cosine G over LT minus, because minus, you have minus here, minus I sine LT. Obviously you can factor out cosine with cosine and sine with sine. I'm just doing here, gonna be A plus B cosine G over LT plus I A minus B sine G over LT. Obviously you can say this is a constant C1 and constant C2 because A and B, they are in nature, they are in complex. So doing that, you can write generally solution as D sine G over LT minus phi. And this is trigonometry. This is not control. This is not vibration. D is C1 square plus C2 square. And the phase, this is phase angle. Please do as a homework. You are graduating, okay? Find the phase angle based on C1 and C2 for me, for yourself. What's the couch here is? This name of this is the amplitude. Amplitude. And the name of it is the phase angle. Okay, guys, let's back to the first year of the high school. I want to plot the angle of the pendulum with this assumption that there is no disturbance on the hip joints of your body. Angle versus time is sine of something. How it looks like? Harmonic, right? Yes? Like this forever. Yes? Okay. Means that if I release it from some point here with assumption that there is no disturbance, it's gonna oscillate forever. Ding, 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 ding. Clear, everyone? So when you're oscillating, this is physics that you learn, hopefully. You have a frequency of the oscillation. What's that frequency? Here we go, natural frequency. Omega n, natural frequency. You guys that you had passed the vibration with me, you know how we derive that. But you didn't, I'm teaching you here. So this is natural frequency of the system. Why natural frequency? Because it has a physical meaning. Because we are pushing here and we're releasing. Now, based on gravity, system oscillate by itself naturally, natural frequency. See what I'm saying, everybody? Yes? Huh? So, bear with me. I'm going to connect the control now. So, angle of the pendulum gonna be, we saw, is D sine omega nt minus phi. We derive by assumption that there is no the hip joints acceleration. This natural frequency obviously is in radian per second, which is a function of gravity and the length of the pendulum, length of your leg. Okay, you're gonna tell me what's the connecting point to the control class that I'm taking with you. Bear with me, guys. Okay, theta, again I'm plotting here, time, and it oscillates forever. Oscillates forever. You know that this is repeating here. So here is the period, t. You know that the period is 2 pi over omega n. You have it. Okay, guys, you tell me. You want to teach this to your boss that he got degree in management but has no sense of stability, control stability. If asks you, okay, hey, Mike, Elizabeth, okay, is your system stable or unstable by showing this graph? So what you're gonna say? Is your system stable or unstable? Why? Any other ideas? Mm-hmm. Both, both are wrong. Your system, yes, your system is what I told previously, is marginally stable. Marginally stable. Is not stable because it's oscillating. The oscillating system is not stable. Stable means remains at the things that you want to have. okay, is not unstable. Unstable means this, guys, goes forever. Angle of the pendulum physically, look at here, it's gonna goes forever like this. This is unstable, okay? But this is oscillating like this. So this is marginal on the border of stability and instability. We say it marginal. So any system, this is take home message. Any system that the response is harmonic, like a sine, cosine, the system is marginally stable. Okay? Not stable, not unstable. This is your function after graduating from SDSU to design controller, make it stable. This is your function. That's why you're taking this course. See what I'm saying, everybody? Yes? So, let us classify. So when I say marginally stable system, like as the pendulum, I'm going to teach you unstable right now after this, okay? So marginally stable system, what was this characteristic? It has what kind of roots or poles that I'm going to define poles later? What was that? You tell me. Look at your notes. I just taught you. The poles of a marginal system is a pair of pure imaginary roots or poles. This is definition of the marginally stable system. If you see in the complex plane, you have a pair of pure imaginary roots here. Later in a few classes later, we have poles. Just gonna rename everything to poles. Roots gonna be poles. Okay, it means that your system gonna oscillate. It's marginally stable. Example: pendulum. Your leg, your hand. Okay, or your grandmother and father old watches. Now let's go and continue to unstable system. Unstable system. We learned about this marginally stable system. Here we go. The guys that you had the vibration class with me, can you give me the example of unstable system? We learned that the pendulum is marginally stable system. By having a pair of pure omega n, because we said omega n is root square root roots or poles. If I invert this system, ping, like that. What's the name of this problem, guys? I just inverted. What's the name of this problem? This is pendulum problem. This is inverted pendulum problem. These are technical names. Inverted pendulum problem. So I'm skipping how I derive it because I memorized it after being professor for more than 12 years, okay? And this is my field of research. So if you apply the point O, okay, assuming that there is no disturbance on the base, okay? So if I say again, you apply this, moment equation from dynamic course. This is the equation you get this time. After linearization, okay, I linearized, okay. I'm skipping that because it's too much. I'm gonna waste your time. But the equation of this one was this. After linearization. What's the difference between them? Guys, look at just the equations. What's the difference? Only difference they have. Tell me. Yes. Here is positive. Here is negative. When we go forward, you're gonna learn from me based on the Ross stability criteria in this course that all signs of a differential equation in the left hand side must exist and be positive. This is a necessary condition that your system be stable. So one of the sign here is, I'm going to teach you in detail. It's not like that. It has a heavy math behind it. One of the signs in the left hand side is negative. This signs you like as the alarm, ding, 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 ding. It says your system is unstable. I'm gonna teach you why based on the Ross stability criteria. But for simplicity again, E is ST, and if you put theta double dot, now you know it is S square EST, and you replace here and you factor out as we did previously. Is S square minus G over L is 0. This cannot be 0, obviously. So you have again two roots. But the two roots are this. Real roots. Real, not imaginary. Real. Two real distinct roots or poles later. I'm going to teach you after Laplace transform. If you put it here in the general solution, theta of t gonna be a e plus g over lt plus b e minus g over lt. You cannot use the Euler, because Euler, where is the Euler? Euler is for I, imaginary part here. We don't have it. What is that? Yeah. So this is the solution for the inverted pendulum. There we go. Let's go back to high school. When I increase time to infinity, what's gonna happen to this? Come on, guys, tell me. Don't disappoint me. What's gonna happen to this? This goes to how much? 0. Everybody agree? Yes? And this gonna go to where? This is plus infinity. So if I plot it versus time, it's gonna be increase angle forever. And your system is unstable. Remember, for margin stable system, let me not the green, but with the blue saying kind of okay. Margin stable system, you are this. For unstable, let's back to the control concept. I want that you have a solid foundation of the control. Math, coding, simulating, everything. Imaginary, real, complex plane. For the margin stable system, you have the pair of pure imaginary roots or poles. But for unstable system, you have these guys. Two distinct, one of them positive, one of them is negative. So let me change this. Or let me change the color of this to blue, saying marginally. and the red means danger, means unstable. So you have, say here, positive plus root square of g over L and negative. Huh? So take home message. If one of the roots, write it down, everybody. If one of the roots, later we're gonna name it poles, are at right hand side of imaginary axis, your system is what? You tell me. You tell me. Unstable. Unstable. Now you are learning control, fundamentals of control. We know that if you have a pair of pure imaginary poles or roots, your system is marginally stable. Means physically your system gonna oscillate forever. But when you see this, at least one, because you're gonna have third order system, fourth order system, 10th order system, means you have 10 poles, 10 roots. Maybe you have many here, many there. And what's your function? To design a controller to push this to the left hand side. This is your function as a control engineer after graduation. Is to design that box of controller to push this to, I don't know, to here, say. This is your function. So if you want to have a stable system, now you tell me, you teach me. All the poles must be where? Must be where? All roots, you tell me. All roots or poles must be where? Left or right? Oh, yeah, must be at left hand side of imaginary axis. Then your system is stable. This is very, very practical way of making understand the person how from a nonlinear differential linearizing around the equilibrium point. What is the equilibrium point? Using Taylor series expansion and then linear differential equation and then solving that and then judging about the roots or poles, complex plane, about the stability, instability, or marginally stable system. So if I want to compact in a CD of in your mind, okay, if you have a system like this in complex plane, you have this kind of the poles. Let me change the colors. The green ones are on the left hand side, huh? Say. They are for different systems. That's why I changed the colors. The green ones means they are system you are stable. For another system, if you have this one on the imaginary, means your system is what? Marginally stable. If another system you have this kind of things, means oops, your system is unstable. You're gonna design PID controller on the graduate level, lead lag controller on the graduate level to push this one, even this one, to the left hand side. The whole history of the control is this. Going to the left, left, left. Understand? Everybody? Yes? Huh? Good. So, now let's go to the MATLAB. But before that, I have to teach you about the state space. State For those of you that you are not aware of that from my vibration class, state space representation. How many of you are aware of this? I taught in the vibration course. Because MATLAB coding is based on this still, state space representation. MATLAB is good. Okay, let's do that. So it's theta double dot plus omega n square. Now we know what's omega n. Of sine theta. I'm keeping nonlinear now. Nonlinear. Okay. Minus, now we have the moving pendulum, x double dot over L. And here is cosine theta. Cosine theta. The state space means that you assume, as I'm doing exactly, I'm going to copy and I'm going to write in the code in MATLAB. Because at the end of this course, I'm going to use this example exactly to add the controller and show you how the control works. For this and for robot, okay, at the end of the course. So state space, I'm saying that this is state variable. M1 is the angle of the pendulum. And the M2, I'm going to type in MATLAB, is angular velocity of the pendulum. If you are talking about the temperature of a room, it's gonna be T temperature. M2 gonna be what? T dot. If you are talking about the pressure of a tank control, gonna be P, and M2 gonna be P dot. If you are controlling a kebab, it's gonna be kebab, Persian kebab, and the M2 gonna be what? You tell me. Huh? Kebab dot, time derivative. Okay, understand? Now we are talking about only the angular position of the pendulum. Okay, let's do that. Have a time derivative from both sides. Exactly, I'm typing in MATLAB. So dm1 time derivative gonna be theta dot. What is theta dot, guys? You tell me. What is theta dot? What is theta dot? Based on the state variables. This is M1 and M2. What is theta dot? What is theta dot? Huh? Guys? What is theta dot? Can you read this term in this box? What is theta dot? Guys? Can you read this box? Orange box? Anybody? Yes. Not magic. Yeah. So M dot 2, lady, control and math is super important. Just depends on your glorious professor like me. I'm just joking. So it's gonna be theta double dot from the second line. What is theta double dot? You tell me from this equation. What is theta double dot? Gonna be minus x double dot over L cosine theta minus omega n square sine theta. Yes or no? Not magic. Right? Right? Everybody? So what is theta based on the state variable? You tell me. What is theta? Based on this box. Yes. Minus x double dot over L cosine M1. I'm going to exactly write this in MATLAB encoding. Minus omega n square sine M1. The name of this is state space equation, meaning that say bye-bye to this and bye-bye to this. Just keep as state space, as state variables M1 and M2. So your state space equations in MATLAB gonna be like that. dm1 is equal to m2, and dm2, this is how we write in MATLAB, is minus x double dot, exactly I'm gonna type in MATLAB, cosine m1 minus omega n squared. We're going to define this in MATLAB. Just bear with me. Sine m1. You get it? Yes? See? No magic. Let me go to MATLAB. Exactly type this in MATLAB and make a simulation of your moving pendulum. And make a movie of that. And then I'm going to teach you in which part you have to add your controller. MATLAB. Maybe I'm going to do the first part if I have time. I'm going to continue the Thursday. We're going to complete this, okay? So M1 and M2, their names is state variables. And the name of this equation is state space equations, okay? Oh, this is from the vibration class from previous semester. Let me close this. Okay, you're gonna go to MATLAB when it comes up, new script. This is how we write. We're gonna say function. It comes blue. Can you see, everybody? So I promise you I'm gonna do that. I'm gonna say DMs. You have to define it here. DM equal to, give it name. I'm gonna say control class pendulum for now. Stability concept. So what parameters are involved here? You are engineers. DM means time with respect to time. So time, T. MATLAB knows this. Time, T. And state variables, M. We define M1 and M2. See here? Exactly how we write M1 and M2. Bear with me. Here we go. You have to save this. When you put Control S, save that, and then I'm gonna go to ME530, and this name must be exactly, guys, this name, exactly. If they are not, it's gonna give you syntax error when you write your code in MATLAB. You got it, everybody? This name exactly must be this name. Don't change it. Here we go. Then you're gonna have DM equal to zeros, 2 and 1. I hope that you passed MATLAB. Zeros, 2 and 1 gives you a rows of zeros. 2 rows of the, see here? 2 rows of the zeros. Why? We have 2 state variable. If you have 5 state variable, I'm going to show you have 5. Look at here, guys. Like I say 10. Say 10 state variables. So 10 rows of the zeros. You are making space for all the state variables. I'm going to share this after the class. Okay? To your emails. Don't worry. Control S. Okay, let me write it down. The equations. dm1 is equal to m2. Exactly what I'm typing here, guys. dm1 equals to m2. dm2 equals to minus. I'm saying disturbance. Look at here, guys. Because mine x double dot was disturbance, remember, in control class. Minus disturbance divided by L, length of the pendulum. Length not to, it is nonlinear still. I'm gonna compare with linear also here. Sine M1, as I promised. Look at here. Cosine M1 minus this cosine. This is cosine. I'm just typing cosine because MATLAB knows sine and cosine minus omega natural frequency. Omega n natural frequency, I'm writing like this, square multiplied by sine m1. Here we go. Now we have to define those. I say length of your leg is 1 meter, and this is, I put here system is in meter. When you put this sign, it's gonna comment that. Okay, this is length of pendulum, and D disturbance. Okay, let me do that for you. Look at here, guys. No magic. Let me go back here. Okay, guys. This is the pendulum. I said there's a disturbance x. I'm saying disturbance is harmonic. Do you care? Sine of t. So x dot gonna be cosine of t from high school. X double dot gonna be minus sine of t. So your x double dot is minus sine of t. Here we go. We're gonna put it here. I'm going defining with d. Okay. So going back to the code, I'm saying d is minus sine of time because t, because you already MATLAB knows the time. I'm going to teach you how. Okay. So we define d. This is disturbance of the system. Disturbance of the system that you have to design control at the end of the semester rejector. So and the omega n. Omega n was root square SQRT. This is the command in MATLAB, root square. Gravity divided by L, G over L. So you have to define gravity. Gravity is in the surface planet is 9.81, obviously meter per second squared. This is definition of that. This is natural frequency, natural frequency. Here we go. You got it? As I promised, you see here. Everybody? Yes? Huh? Okay. Now we have to solve this space that says equations. So I'm going to stop it here because I have to extend the code. I'm going to develop the code. And next class on Tuesday and Thursday, we're going to finish this and then I'm going to move to Laplace transform. I'm going to connect this why we have to go to Laplace transform of frequency domain. This is how we define differential equation in MATLAB and control aspect of that. Okay, guys?